La mise en route du four solaire est simple et rapide. Le châssis étant orienté par rapport au nord, il suffit ensuite de positionner le point de chauffe et d'armer le ressort qui va entretenir le mouvement. Le mécanisme se veut simple, robuste et insensible aux intempéries. Voici quelques exemples de cuisson. Début novembre, avec écran de limitation de puissance et ciel légèrement voilé. L'énergie est encore suffisante pour une cuisson lente. Mi-novembre avec plaque de fond vitrocéramique. La température à l'intérieur du four atteint les 260 degrés. Il faut cependant noter qu'en présence de forte évaporation, cette température peut chuter de moitié. Le mécanisme de guidage permet le positionnement de la parabole afin d'obtenir un point de chauffe immobile dans l'espace et une direction du faisceau solaire toujours verticale. Cette configuration permet de réaliser de manière efficace tous les modes de cuisson. Le mécanisme, basé sur le contre-mouvement terrestre, va faciliter la conception du système de commande, à savoir un actionneur unique, à vitesse constante et à faible couple. Plus besoin donc de systèmes compliqués à base de calculateurs électroniques ou de trackers solaires. Dans cet exemple, un simple mouvement d'horloge suffit pour réguler la vitesse de la parabole. Si la parabole ne constitue pas une nouveauté, il faut cependant noter deux points particuliers. D'abord, la surface paraboloïde est déportée vers le bas par rapport à l'axe focal. Ceci permet de redresser le rayon solaire vers la verticale. Ensuite, la surface est constituée de facettes. Ceci permet de répartir de manière homogène l'énergie solaire sur une surface déterminée. Cette énergie peut être ajustée à l'aide d'un écran. En période hivernale, ce n'est pas la température extérieure qui limite l'usage du four, mais plutôt le déficit solaire.
Les bons vieux panneaux solaires seront-ils bientôt dépassés? À la station d'épuration de Suncalor, la société Axiosun teste le solaire à concentration. Le principe, de grands miroirs incurvés qui suivent la course du soleil et concentrent les rayons sur de petites cellules photovoltaïques.
C'est ce que vous voyez ici, ces petites barrettes là. Et sur ces petites barrettes, nous allons concentrer, grâce à ces miroirs aluminium, nous allons concentrer le soleil et nous allons produire autant, grâce à cette concentration solaire, sur ces petits modules que sur des grands panneaux photovoltaïques que vous pouvez connaître, par exemple, en toiture.
Ici, on produit 4 kW, ce qui pourrait couvrir la consommation annuelle d'une famille en électricité. Cette installation nécessite moins de cellules photovoltaïques, donc moins de matériaux polluants. C'est surtout moins coûteux que le solaire classique, jusqu'à 20% d'économie par kilowattheure.
It's photovoltaic technology, but the achievement is that we separate out the collection function of a photovoltaic cell to the light conversion to electricity function. And we collect the light, instead of using a huge area of solar cells, we use an equal area of cheap glass mirrors. and they are curved in such a way as to concentrate the light onto a very small solar cell, the size of just one cell. And in this way you concentrate the light 1,000 times, and you can get 1,000 times more power. The average person who lives in a sunny area, perhaps the desert of California or Texas or New Mexico, Nevada or Spain, Italy, south of France, North Africa, anywhere in the Middle East, would be able to put a dish in his garden about 10 square meters, that's about 3 meters by 3 meters, and generate most of the home's electricity needs. And for big power companies, utilities, they could build fields, tens of square kilometers, to provide large percentages of the country's electricity requirements. I think you can solve the energy problems of many countries, of essentially all sunny countries.
He's built a new, tiny solar panel that holds unprecedented amounts of heat and transforms it into electricity. Using this dish, essentially a giant mirror, he concentrated the light of 1,000 suns onto the new panel. The result was staggering.
So these ones here produce 1 watt.
1 watt each, yes.
This one, 1,500.
Yeah. Mm-hmm. Amazing, isn't it?
These ones here produce 1 watt.
1 watt each, yes.
This one, 1,500.
Yeah. Mm-hmm. Amazing, isn't it?
Now we'd like to show you the prototype machine. We use the prototype machine to develop the technology for the pump that we're taking to Haiti. We're going to operate it in 2 different modes. We're going to operate it in pendulum mode, and then we're going to disconnect it, and we're going to operate it strictly as a lever arm pump. What you're going to be able to see of what we developed after a lot of different tests is that the fatigue factor in operating it in this manner or a rotary manner is very easy to operate. And then when we disconnect it, you'll see that it's very hard to operate strictly as a lever arm pump. And now you can see that we've disconnected the piston drive arm from the pendulum pump, and we have the pump set up strictly as a lever arm pump. It's interesting to note that the lever arm is 16 inches long, which is the same setting that we had on the pendulum pump. It's also interesting to note that when I pull the lever arm back and forth, we're going 1 inch. And you will also note that when we're going 360 degrees or back and forth in a horizontal position with the pendulum pump, we're going the same distance. Now here we go. We're going to show you just how hard it is to pump with strictly a lever arm pump. You can see that it's not easy. Even if I want to use 2 hands, I don't want to do this very long, so give me gravity-assisted power any day of the week. Oh, that's it for me. This is where the water comes in. This is the first chamber inside the pump. The pump goes in these 2 chambers. This is the drive mechanism that drives back and forth. By changing these pin settings here, I can pump high pressure, low volume, or low volume, high pressure. Right now I have it in a setting here. This is a 1 inch setting, so the pump will go back and forth 1 inch. This is the discharge side, so the water goes out of there. When it goes out of there, it goes in through this filtration system, which is 3 stages. I can put any type of cartridge in here that I want to pump clean drinking water. If I need even purer water, I close this valve and it'll go through reverse osmosis equipment, which will remove dissolved solids from the water and make water pure enough to be able to use in a hospital. The last cartridge in the filtration system will kill microbes. It will also kill viruses and spores. So it will be fit to drink. It meets drinking water standards.
So how do we clean the water for entire villages or communities without a large-scale water treatment facility? By using the revolutionary gravity-assisted Feltenberger pendulum pump and AquaThin filtration system. Gravitational Energy Corporation has teamed up with AquaThin, a highly recognized and proven water filtration industry leader for over 30 years, to produce a simple-to-operate water filtration system capable of producing over 1,000 gallons of pure, clean drinking water per hour. Don't let its small size fool you. a single Feltenberger pendulum pump is capable of providing daily enough clean drinking water for up to 40,000 people. With this simple hand-operated device, virtually any polluted water source can be filtered and transformed into clean drinking water with very little fatigue to the operator.
Well, this is our newest pendulum pump, and it's our most portable and the easiest machine to move about. It's built permanently on a heavy-duty trailer, and it's very easy to tow it about with a truck or a Jeep, or it can be moved by hand. It features the same things that are on the machine that we sent to Haiti that is pumping clean water for people there. On this side, we have the AquaShield filtration system, and on the other side of the machine is the reverse osmosis system. And this way, being portable and having the ability to make clean drinking water as well as ultra pure water, we believe it can service the needs of thousands and thousands of people.
I'm here at the Feltenberger pendulum prototype, and I'm going to get this thing moving. So let's see what happens here. Just kind of a little bit of pressure, not a lot, and it kind of takes over. It's swinging, and I think this is the position you wanted it at.
That's right.
So I can do it with a couple of fingers here. Not a big deal.
Well, Dave, this technology is really quite simple. This is an early machine that we built. You know, in the inventing process, you go from an idea, you put it on paper, but then it would be nice to be able to show it to people and let them feel how it works, such as you're doing here. So this is an early prototype. Actually, it encouraged us to go forward with additional work. And you'll see, much like the gravity-assisted power found in hydroelectric power plants, we operate with taking energy from a falling body also. In this case, it happens to be a pendulum. And then the heart of the technology lies in this area where we cause it to move in another direction, okay? It communicates with the swinging of the arc, and it goes in a straight line, and we're then able to transfer that into the piston in a reciprocating pump. And that can be used for a variety of purposes, such as pumping hydraulic fluids, pumping water, and so on. And in this case, we've developed a machine here that can lift weights to show us exactly how much work it's doing. So I'm going to go ahead and engage the workload for you. And it's currently now lifting 60 pounds. And I think that you would probably agree that it's not very difficult to do that. You can probably barely notice the change.
I don't really feel any difference at all. Well, Bruce, you built the prototype. Then you had some data that was real-world data.
That's right.
What'd you do next?
Well, the next step was to apply for a U.S. patent, which we received. And in the course of refining the machinery, going from this prototype stage, we were then able to improve on this process over here, which allows us to push the pendulum all the way around 360 degrees, or less than that, like you were doing, and still achieve this motion right here. In the course of doing that, we also found a way that we can adjust for how far this moves, so that we can change a selector pin and allow it to create greater volume or greater pressure. And because of that, we were able to attach water filtration systems to our machines so that we can pump water and clean it up, make it safe for drinking. And if you need even cleaner water, we've added a reverse osmosis system, which requires greater pressure, and we can power that also. And because of that, we put together a machine that's a little bit bigger than this one and obviously more refined because this is a prototype. But that machine was then donated to the earthquake victims in Haiti shortly after the earthquake last year, where they've been successfully using that machine about 3 hours a day to produce safe drinking water for about 4,000 people daily.
So water for 4,000 people in just 3 hours of a day. I can see if this could have application in natural disasters all over the world.
Well, yes, you're absolutely right. As a matter of fact, we're currently in the process of building 2 machines for a Northeast Ohio firm for use in an emergency management program, as in the case where you maybe have tornadoes or floods or earthquakes like in Haiti or more recently Japan. And the machine will be able to produce a lot of clean drinking water. We're also now developing an attachment for that same machine, which can generate electricity for use in recharging of cell phone batteries and lighting of LED systems and that sort of thing.
So this system can be used to generate electricity?
Well, yes, it can, Dave. In addition to generating electricity by hand, the same technology can also be used on a much larger scale. As you saw on our large pendulum when you came in, that machine is 18,000 pounds, and based on various tests we've conducted, we believe we can generate commercial-grade electricity with that machine and do it while we're using a lot less fuel than what other systems require. We're hoping to get down near 50% of the fuel. So we would reduce the fuel or use the same amount of fuel and produce twice the electricity. In fact, in normal power plants, the efficiencies are only around 40 or 45%. So there's a lot of room for improvement.
Olivier Paco will now push the button.
Sunpulse is exactly the same. Has 2 pistons, have one hot heat exchanger, one cold heat exchanger, one regenerator, a crankshaft and a flywheel. But it's arranged in another way. This is a cut view through the Sunpulse. It's a big top, a big pot with a funny shape. And in this pot, the heat exchangers are arranged concentrically. Here I will first put the heater. This is copper tube. Maybe we can imagine if we look from the top. It will look like that. I make only the half of it. So this will be the heater, it will be here. And here we have the... Okay, this one is exactly this one, huh? From the top view. And here, this is a cut view. So this means we have in a circle about 10 little copper tubes, and we have on this copper tube the aluminium fins. This one. The water will come. In our case, it will come here, and it will make the complete circle and come back at that place. For example, we don't see it because it's a cut, but it's cut. And here we can see the aluminium fins. So this is the hot place inside. Now we can make the same concentric for the cooler. And here it is here. From the top view we have the cooler at that place. With the aluminium fins. This place, it's about 50 millimeters. It's a big ring of 50 millimeters and about 250 millimeters height. Is filled with this stainless steel wool regenerator. We have our 3 heat exchangers, so we can imagine the air can work like that. Air can pass in this direction and again in this one. In order to move this air, we need, of course, the displacer piston. So that's the same shape, the conus than the bottom, like that. Well insulated, because it is making the separation between hot place, hot, and cold. Now, this piston will be as a rod and it will be actuated from here. But of course, we have a big gap here. We have no ceilings. And in a classical engine like that, you will have here some ceilings or piston rings or something like that. And in our case, with the Sunpulse, we have here a membrane out of cloth. Fix it here at the top of the heater to the piston. So now when we move this piston here, the membrane will roll and make like that and go.
So basically you're moving this from here somewhere up to here.
We have the same here, we have the outlet and inlet from the cooler. The cold water is flowing inside here in a cycle, concentric, and comes outside. Now what is missing is this one. We are producing now hot, cold, high pressure, low pressure. We need to use these pressure differences, so we need the main piston. The main piston, it will have about the same shape. Now we see we have a gap here, so we need a sealing too. Here we have a classical sealing, and here we have a membrane too. When the piston is moving up and down because of the pressure fluctuation, this membrane will roll on itself. This is the piston, this is the Sunpulse. Okay? And now, just imagine you have the same in the opposite way, because this membrane is inflated, so you have a double layer. You will have a hose which will make like that. So you have no friction, you are not tearing, or so the membrane can live for a very long time. This membrane will be filled. We have a little mechanism inside, which will fill it with the maximum pressure of the engine. So it will be always, as soon as the engine is working, this membrane is inflated, so it's working smooth without noise. And the main piston have such some bars here. And here we have, I would say, let's say we will make the shaft, and here the flywheel. On this shaft we have the excenter, and here we'll have the big connecting rod to the piston, here, to the piston housing. And here we have again a little mechanism to drive the displacer piston.